day of chapter 7, then we're going to move on to 8, which is also probability, but just talking about it a little bit differently. So today we're going to talk about conditional probabilities. So there was that question that back, I think it was on Monday, I said you wanted to find out the probability that you have a disease given a positive test. Like that's the kind of question we'll be able to answer. And we're going to learn a rule today that lets us flip that conditioning. Because we found that probability of A given B isn't the same as B given A, right? Those are two different things. It's not commutative. But we'll be able to change this using a flipping argument and some other probabilities in there. It's called Bayes' rule. And I'll teach you 3 different ways to do problems like that. Okay? They're all related to stuff we've already done. So you can have conditional probabilities that can be given directly. And when we first started talking about these, we had an example that the probability that a 9th grader is a gambler given that their female is 0.045. So probability of gambler given female, we were just told that's what that was. You just have to be able to interpret that from the context of the problem that you're reading, which can be tricky. Or it could be the case that a physical situation makes it easy to figure out the probability. For example, that shouldn't say that should say what, but spell check won't catch that. What is the probability that the second card drawn from a 52 card deck is red, given that the first card is red, and assuming that we're operating without replacement? Okay, so probability of red given the first card was red. So how many cards are red in a 52 card deck to begin with? 26, half of them. So if you've already taken a red card out, how many red cards are left to choose from? 25 out of how many cards total? 51 because you've already taken one away. Does that make sense? You've taken out one red. So the chances the second card's gonna be red is just 25 out of 51. Because that's the number of reds left divided by the number of cards left. Number reds left divided by number cards left. Does that make sense? Okay. Now the other way we found conditional probabilities was using this rule, right? This is what your book called it Rule 4, but it's also a restatement of what they had for Rule 3A. So what Rule 3A had is it just had the P of A over on the left side instead of in the denominator, and it had the P of B over on the left side instead of B in the denominator. That's just like multiplying by it gets it out of the denominator, right? And I think the thing that I told you to help you remember how this goes is that the second thing in your condition is the thing that goes in the bottom, right? So if you have B given A, it's A and B divided by P of A. If you have P of A given B, A and B divided by B. And A and B is the same as B and A, that's why the order doesn't switch there, right? Just who cares? Okay. So we're going to use that one to do example 1. So suppose that a college course has a midterm and a final. From past experience, the instructor knows that the probability of a randomly selected student will get an A on both exams is 0.15. And the instructor also knows that the probability on the midterm is of A on midterm is 0.25, and A on final is 0.20. So suppose the student earns an A on the midterm. Given this information, what is the probability of getting an A on a final? You know that students get A's on midterms are more likely than the average student to get an A on the final, right? Okay. So we're looking for a probability. Well, should we do this? Probability A on final given A on midterm. Are we looking for that one or this one? Which one? The first one. The thing that comes after the bar is the given, which means it's the thing that you know. You know you have an A on the midterm, right? That's what you're given. Okay. So using that rule above, how do you translate this? You say probability of what's in the numerator? A on midterm and A on final, right? So probability of A, can I just say A on both because that's the same thing as and? Okay. Divided by probability of A on midterm. And I think you were told all those numbers. What's the chances of A on both? 0.15. And on the midterm? That's the same thing as 15 over 25, isn't it? Which reduces to 3/5 or 0.6. What I really should have done if I was being a really good teacher was computed those probabilities from my class specifically, because that would have actually been kind of interesting. But there you go. 0.6. Everyone okay with that? Okay. So all of that's kind of stuff we already did. The next one's going to be a little bit different. This is called Bayes' rule. So a common situation in probability occurs when you know conditional probability in one direction, but you want to know it in the other. So that's like the example that we had is you may know how accurate a medical test is. What that is kind of saying is probability of a positive test given that you do not have some disease. Because I assume, because I generally speaking do trust doctors and researchers, that before any kind of test is used for some kind of medical condition, they probably have to have done some kind of study and they have to have an estimate of what this probability is. They have to know how accurately are you going to get positive tests when you don't have the disease. You know how often that should happen approximately. That's called a false positive. Does that make sense? But what you might want to know, because you go to the doctor and you have a positive test and you're like, holy crap, I want to know what is the probability that I do not have the disease given I know that I have a positive test. Because having a positive test is going to increase the chances that you do have the disease relative to somebody who had a negative test, right? So knowing this information is going to make this probability higher, but the question is how high? And how high depends on how accurate your test is. Okay, does that make sense? And we want to flip these two things. Did you have a question?
I was going to ask with the false positive, like if you took the test again, would that...
That's actually why you often should ask for a second opinion on stuff, because if you take the test again and you get conflicting results, then you know that something is up. You should do it a third time and figure out who wins. So, yeah, definitely. But I'm not a medical doctor, so I make no recommendations as to what you're supposed to do with your health, okay? There, liability released on video. Okay. All right, so here is what Bayes' rule says. So this is a lot of probabilities that get put together. So the first thing is that this is just the rule that we already know, right? That's the rule 3 that's given above. Everyone okay with that? Okay. This next thing, that comes from, we know P of B given A is equal to P of A and B over P of, wait. No, that's right, I said that wrong. P of, what should be in my denominator then? A. P of A. And you see if I solve for P of A and B, I get P of A and B is equal to P of A times P of B given A. So is it clear where that numerator came from? Okay. And the denominator didn't change yet, right? They're okay with that so far? Okay. Now then, what they're going to often use for the denominator is they're going to say, okay, well, B, you can find that probability by finding the chances of A and B, or A complement and B. And I think that's best explained with a picture. So you have some space down there. Draw yourself some bubbles. You got the A bubble, and you got the B bubble. Probability of B is kind of like the size of the stuff in B over the total size, right? So if stuff is in B, the statement that I boxed is saying, okay, well, that stuff is either in A and B, which is what part of this picture? The middle part. So that's here's the A and B part. Okay, now A complement in B. A complement is all the stuff outside of A, right? I'm going to shade that in yellow because yellow is not very dark. There's all the stuff outside of A. Does that make sense? And inside of B. So where's the stuff that's all outside of A and inside of B? Yeah, so that gives you this part. Does that make sense? So that's how that works. Either, if you're in B, you're either in B and A, or you're in B and A complement. And if these things don't overlap, then this first one's just going to be 0, right? So, whatever. It accounts for all the cases. So, okay, that step so far? Okay, and then the last step, sometimes based on the conditional probabilities you're given, you can change that to this. And so P of A and B, that's the same as what the numerator was, right? And I changed the numerator to P of A, P of B given A. That's P of A, P of B given A, right? And then look, the next one, it's just that instead of A, I have A complement, right? So if I had P A complement and B, it would be P A complement, P B given A complement. So it just is using that same rule for the numerator again. And the thing that you should notice is that if you use this rule, it was A given B, right, to start with. Now it's B given A, B given A, and B given A complement. So it flipped the reversal there. And then you can often compute those reversals and then find the probability you want to find. And the problems that are on your homework like this, they break it down. Like they have you find all the probabilities that you need in one step, and then they have you put them in the formula in the second step. Does that make sense? Okay, let's do one. Okay. So there's one thing I forgot to put in the notes. The test is 95% accurate. If we didn't know that, we would not be able to proceed. So we have some person, and this person had a positive test result for some kind of disease. And if this were you, you were most interested in finding the probability of having the disease given the test was positive. And we're going to find this using this Bayes rule. So just to make my writing less cumbersome, I'm going to let A be the fact that she has the disease. A complement then is that she does not, right? Does that make sense? The probability that she has the disease, we suppose we know that's kind of rare. It's like 1 in 1,000 people. Does that make sense? So the probability she does not have a disease is 0.999, right? And we're going to let B be the test is positive and B complement B the test is negative. And I forgot to put in the notes the test is 95% accurate. What that means is that if you have the disease, it finds it correctly that much of the time. And if you don't, it says you don't that much of the time. Okay, so let's start by writing down the Bayes rule formula. And we'll talk about all the pieces we have to find. So P of A given B. And is that what we're looking for? That's disease given positive test.
No, for the opposite.
I think that's what we want. What you're thinking is that we know the opposite. So we know the probability of the test is positive if she has the disease, but we don't know this way. That's what we want to find. Okay, so that's P of A and B over P of B, which breaks down into this ginormous thing. P of B given A, P of A over P of B given A, P of A plus P of B given A complement. Okay. So let's find, we know some easy ones. So we know P of A. And let's also discuss what that means. So A is that you have disease, right? So probability of disease is equal to what? 0.001. We also know P of A complement, right? Probability of no disease is 0.999. Okay. Now, if you're going to plug stuff into this, you need to know this B given A thing, right? Okay, so P of B given A. That's probability of B means you have a positive or negative test. Positive test given have or don't have disease. Have. Right? Because A is having the disease, right? Okay. So if your test is 95% accurate, what's the chances you're going to have a positive test if you have the disease? 0.95. Because that's the test being accurate, right? It tells you the right thing. You have the disease and you get a positive test, right? Okay. P of B given a complement, probability of a positive test given you have no disease. Yeah, 0.05. Good job. Does that make sense why? Mm-hmm. Yeah, because if you either have the disease or you don't, right? When you get a positive test, you're either in this one or that one. This is the opposite of that event. Okay. And then plug everything in. So P of A given B equals. So what goes in for B given A? 0.95. P of A is 0.001. Great. Over 0.95. 0.001 plus 0.05. And what goes in for A complement? 0.999. Okay, great. When you put this in a calculator, because at this stage you totally can, where do you need parentheses? The numerator or denominator? Denominator. Otherwise, it won't put everything in the denominator. Like if you want to punch it in one go, you put parentheses around the denominator. That ends up being, it's ridiculously small, 0.019 or 1.9%. Does that surprise anybody?
That's not ridiculously small.
It's a ridiculous. So it means if you get a positive test for a medical thing, it might not be the end of the world. Like it might be a false positive, and that has to do with what number comes out of this has to do with how accurate the test is, right? If that test had been more accurate, like instead of being 95% accurate, and it was like 99% accurate, then this would definitely be bigger. Does that make sense? Mm-hmm. So, and it also matters how rare the disease is. So those things all come into play with this. Isn't that kind of a cool example? That was definitely lower than you thought, right?
Mm-hmm.
There's a problem that apparently, I read this book, Statistics Done Wrong, and they gave this question to like kids in med school, and like 80% of them like got the question wrong. I mean, I would have too before this class, so I mean, it's uncannily wrong. So this is not the only way to do it, and your book teaches two other methods. One is doing something called a hypothetical table, and then looking at the numbers in the table to make probabilities, which I think is actually a bit easier. But there are going to be problems in your homework that ask you to do things all three ways. Does that make sense? You just have to try to use them both, and I promise in your test you can use whatever the heck you want, okay? Unless I ask for different things in the directions. But it just depends. I mean, anyhow. So sometimes what you do is you pretend like you know these probabilities, and you say, okay, well, suppose I had 100,000 people. How would they fall into these various categories? So that's called a hypothetical 100,000 table. And the number 100,000 is chosen because often this means you have whole numbers when you do the computations. If you don't have whole numbers, leave them as decimals, because otherwise you could have rounding off error that happens in your answers. So I'll do that in this next one. So we're going to make a table with 100 students for this situation. So we have Magnets High School that includes grades 11 and 12. And half of the students are in each grade. 60% of the seniors and 25% of the juniors are taking calculus. So you could use Bayes' rule for this, as not a problem, but we're going to make this hypothetical table. So suppose, and the probabilities that you get will not depend on how many total things were in your table. When you do the ratios, that part kind of flushes out in the end. My table is way too small. Okay. So this is going to be a 2x2 table like we had in chapter 4. So you have two classes, and then you have two things happening in those classes. So you have juniors and seniors, right? Does that make sense? So I'm going to make grade 11 up here and grade 12 here. It doesn't matter which way you orient stuff. If you made those into rows, that's also fine. I'll just have to label them, and then I can interpret it. It's not a problem. And then we have calculus and no calculus. And this is a problem, I'll admit, that I took out of the book and I modified the numbers so I could still give it to you as a homework question. And I modified them in such a way that I won't get whole numbers anymore, but your textbook problem, you still get whole numbers. Okay, so the first thing that I know is that there's they have 100 students in this school, hypothetically, and half of them are in each grade. So it tells you that if you do the grade 11 total, what's it got to be? 50, and it's also to be 50. So that's got to be 50, and that's got to be 50. Does that make sense? So the first thing in these tables is to figure out what total you have. Okay. Now the next thing I know is that 60% of the seniors and 25% of the juniors are taking calculus. So I took this 50. How many of them are going to be in calculus? How would you figure that out? 60% of them, right? So 50 times 0.6. And I think that comes out to be 30, right? Okay. And then how many are not in calculus then? 20. 25% of the juniors are taking calculus, so that's going to be 50 times 0.25. And that's where my fault, this came out to be 12.5. That was not on purpose. Okay. But we'll leave it as 12.5 because that's going to be accurate in the end. And then no calculus, there'll be how many people in no calculus? 47.5? No, I can't subtract today. Must be Friday. 37.5, right? So the total people in calculus are 42.5 in and 57.5 not, right? Does that also add to 100? Yeah. On the notes that I put online, I just changed the 100 to 200 because then I wouldn't have to deal with half students. Because that'll make this number into, these two both into 100. You just can't do that on the homework if it specifically asks for 100, because I'll be checking if you got the right numbers then. So just follow what the directions say, and if there's halves, just leave them as decimals. So that part not so bad, is it? Okay. Now part B, I'm going to write it on here because I need it, says, suppose that a calculus student is randomly selected to accompany the math teachers to a conference. What is the probability that the student is a junior? So does it make sense that it's probability of junior given that they're in calculus? Because they're not going to go to that calculus conference unless they're actually in calculus. So just use the table. How many, you could do probability of junior and calc over probability of being in calculus. That's just like your basic rule, right? So how many people are juniors and in calculus? 12.5 out of how many total? I think that would actually be out of the 100. We'll get there, and let me just, hear me for just a second and I'll explain in one moment, okay? But this is like over everything, how many people are juniors and in calculus. And out of the total, all the student body, there are 12.5 people in calculus out of the 100 people in the student body.
But they asked out of everybody, where are the odds of the juniors going, right?
Yep. We'll get there. We'll get there. What's the chances that everybody's, somebody's going to be in calculus? How many people are in calculus? 42.5 out of the total number of students, which is, so do the hundreds matter?
So you can take out the hundreds.
So you take out the hundreds, and you can just say, oh, looking at just my calculus row, right? There are 12.5 people in calculus, right? Out of a total of 42.5 students in calculus. But that really came from this whole junior and calc over calc rule that we have from like on yesterday. You see that? But the shortcut is you don't have to worry about the whole total business. You can just think, okay, I have this many juniors in calculus, I have that many calculus students. So you do 12.5 out of 42.5, which is 0.294. Okay. If you want to try to challenge yourself, you could try to do that problem with Bayes' rule, like define events and use the same rule. But personally, I think the table is a little bit easier. Do you agree? Okay. There we go. That one's done. Okay. So this was the study that we had about Minnesota. Do you remember this for a little bit? Vaguely? It was like they surveyed people and they found that about boys gambled a lot more often than girls. Does that ring a bell? Okay. So we want to find these probabilities, and we're going to just reconstruct what that table was from the probabilities themselves. So, and I know that they're not teams, they're teens. But, you know, that happens. So 1,000 teens. So I'm going to make a new slide and go back to this and then fill in the probabilities in a second. So big old table. So we have boy, girl, and then we have gamble and don't. And you really can make up whatever number you want for your total. As you saw, the whole over 100s business was going away in the last problem, right? But they say to use 100,000. That's just to give you a number to work with. So you have 100,000 total. Your book is writing that down there in that corner, right? Okay. So, on the last problem, we were able to easily figure out how many 11th graders and how many 12th graders there were, right? On this one, can we easily figure out how many gamblers there are and how many non-gamblers there are, or how many boys there are and how many girls there are? Boys and girls. Because you know that it was 49.1% boys, right? So this total down here is 0.491 times 100,000, which comes out to be 13,534.4. Obviously, that isn't the actual number from the study because it's a part of a person, but it's because we don't have the actual study size. We just made up a number for it.
How did you get that out of multiplying 491 times 100,000?
My calculator told me, did I do it wrong?
You just moved the decimal over 5 spaces.
But there's lots of zeros there.
49,100.
Yeah, what was I thinking? Duh, how did I do that? I don't know. Sorry. What, anyway.
It made me question everything I know.
Me too. Made me think that I shouldn't, anyway. Okay, so, yeah, what do I get there, guys? I even did it like right on the rest of my notes. Oh, it's because in my table, I oriented the other way on my notes. Oh. So of course it's 490, it's 49100, yeah. Guys, this is like basic math. The decimal moves over 5 spots, right? I'm so sorry. 1, 2, 3, 4, 5.
It's not the first time college just made me question everything I know.
Yeah, no, that was me being wrong. I was testing you and you guys passed.
Yay.
Yay, good job. Okay.
Leave now?
No. You passed today. And then it was 50.9% girls. Now I question everything I know about myself. So 0.509 times 100,000.
5,900.
50,900. And does that add up to your 100,000?
Yep.
Yeah, okay, great. Whew. All right. Now, what other boxes can we fill in from information that we're given?
What percentage of boys gamble?
Boys and gamble, yep, so what proportion of boys gamble? 0.229, so we'll do 49,100 times 0.229. That comes out to be 11,243.9. You'll never trust me again now. And what other one can we fill in? The girls, right? And the don't as well.
Yeah.
But the girls would be 50,900 times 0.045, right? That comes out to be 37,856.1.
I don't think so.
You don't think so?
No.
Oh, that's because crap. I really should have checked how my table was oriented. I should really ask you guys to answer all of my questions from now on. So what number is that, guys?
2,290.5.
That's what I got too. 2,290.5. And those now add up to 13,534.4. Okay, boys don't. That's 37,856.1. Do you buy that?
Yep.
Okay. And now those two numbers add up to 49,100. And the girls who don't, that's 48,609.5. Is everyone okay with that now? Y'all caught my mistakes. Okay. Probability of boy and gamble. That's the first dot you have on that paper above where I gave you space for the table. So how many of these kids are boys and gamblers? 11,243.9 divided by 100,000. Let's make a calculator that, right? You get about 0.12112. How about boy given weekly gambler?
You gotta be careful there because a G can also represent girl.
You're right. That would definitely be 0 in most cases, right?
Boy given that girl.
Okay. So boy, given that this person gambles. Okay. How many boy gamblers do you have? 11,243.9. How many total gamblers do you have? Right, there's no reason to actually do the rule. We can just do, we now know we're living in the gamble row, right? And there are that many boy gamblers out of this many total gamblers. So that would be 0.831. So once you know you have a gambler, it's much more likely to be a boy. Does that make sense? Because boys gamble more often. Yes? Okay, what's the last one? Just the probability that you are a weekly gambler, right? So does that specify boy or girl?
Nope, no.
Nope. So how many people gamble?
13,534.
Out of a total of, that comes out to be 0.135. So your chances of being a gambler is just like 13.5%. Probably it's a boy, you know, it's a gambler, is 8.31%.
Minnesota's got a problem.
Hmm?
Minnesota's got a problem.
Minnesotan boys have a problem, not the girls, because the girls are awesome. No offense to any Minnesotan boys who are listening. Okay. It's only a problem, yeah. Only a problem if you lose, you're right. If you can count cards correctly and you can beat the house, then great. There's a great story about people beating the gambling system. Okay, definitely, that will make sense to talk about next week. Or during our review, because that would be a good review of stuff we do next week. It's pretty cool. Okay, so at an Italian breakfast cafe, a waitress has observed that 80% of her customers order coffee and 25% order both biscotti and coffee. So we're gonna let A be the event that a randomly selected customer, that's sad, orders coffee, and B be the event that they order biscotti. So express the waitress's observations as probability statements involving the events A and B. Okay, so first you have the probability that 80% of the customers order coffee. So is that P of A, P of B, P of A and B? Which one? P of A. Probability of ordering coffee is 0.8. Okay, what else are you told?
P of A and B.
Yes, good. You're told P of A and B. Order both biscotti and coffee. As opposed to what the wording could have been is that 25% of coffee drinkers order biscotti. If I'd said 25% of coffee drinkers order biscotti, that's probability of biscotti given coffee drinker. Does that make sense? So let's just write that down so you have practice interpreting that. We'll say if I'd said 25% of coffee drinkers get biscotti, are you given the coffee drinking or are you given the biscotti getting? Or what do you know about the people?
You know they're drinking.
You know that they order coffee, right? That's the thing you're given. So you know coffee. So it's probability of biscotti happening, knowing their coffee behavior. That's what that translates into. And you can see that out. You can see that that is definitely tricky, right? Okay. Part B, we want to know what's the probability that a randomly selected customer will order a biscotti given that they order coffee. So we want probability of biscotti given coffee. And before you try to apply like Bayes' rule or make a table, first go to the most basic rule that you know and see if you can do that. So can you do P of B and A over P of A? And if you can do that because you have the information, go ahead and do it. So do you know P of B and A?
Yeah.
Yeah, that's 0.25, right? Do you know P of A? That was 0.8. So that's 0.3125. Is that okay? All right. All right, last part in this problem says, what's the conditional probability that a customer will not order a biscotti given that he or she orders coffee? So not biscotti with A and B, what's that? B, complement, great. Given A. Okay, let's draw a picture. I think that'll be helpful.
That just be 1 minus.
It's going to end up being 1 minus P of B given A, but the picture is going to help me understand it as well. So here you have your coffee people, right? And here you have your biscotti people, right? No biscotti, knowing they have coffee. So if you know somebody has coffee, where do they live if they don't order biscotti?
In that little like Pac-Man shape.
In that little Pac-Man thing. Yep, does that make sense? What about probability that if you know they order coffee, where is the ordering biscotti part? That's this part right there. So that's why we have the complementing thing going on here. So that is just 1 minus 0.3125, which works out to be 0.6875. And you can think about that logically as well. You're like, okay, if you're a coffee order, either you get biscotti or you don't. Those are opposite things, right? You fall into one of those two categories. Okay. So one more way to do this is using something called a tree diagram. And this is also a totally legit method. I'm going to have you do one homework problem with this as well, okay? Okay, so here's the example. Suppose that in a population of adults, the probability that a woman is taller than 68 inches is 0.15, and the probability that a man is taller than 68 inches is 0.75. Those are actually conditional probabilities. It's the probability of taller than blah given female, or taller than blah given male. Does that make sense? That's what we were told. We know something about you, that's what we're given, and we know something about the probability of being tall all of a sudden. And the population is half men and half women. Okay, and suppose you've got a random person from the population who is taller than 68 inches. Find the probability that the individual is a female. So you want to find probability of female given tall. Does that idea make sense? What do we know? we know probability of tall given female, right, which is the opposite order. So you could use Bayes' rule, you could make a table, that both would work just fine, okay? But there's also this tree method, and this is also, it's kind of a cool method. So your first branch is when you break into two genders. So on this one you have women, on this one you have men. And on the branches of the tree are the probabilities that you fall into either category. So in this case, the population is 50% men, 50% women. So on here is probability 0.5, on that probability 0.5. Does that make sense? So the probability that you go on the first branch is 0.5, second branch is 0.5. And then from there, things divide into more categories. You can be woman and tall or woman and short, right? So if you're a woman, what's the chances that you're going to fall into that tall category? 0.15. And in the short category then, 0.85. Yep. And how about the men and tall? 0.75, we're told that. And on this one, it's 0.25. So far, is that okay? Okay. Now, if you follow a branch, if I follow the woman and then the tall branch, and I multiply those probabilities, it gives me the chances that I'm a woman and I'm tall. So if I multiply along that branch, I get probability of woman and tall is 0.5 times 0.15, which works out to be 0.075. And that, okay, and then what about the next event? How about woman and short? I multiply the 0.5 and the 0.85. So that's probability of, we'll say, W and S. So 0.5 times 0.85, which works out to be 0.425. Is that part okay? One more thing, let me finish. When you add these two events up, you get 0.5, right? And that's the chances of you being a woman, right? Either you're a woman and you're tall or you're a woman and you're short, okay? Let me finish and then I'll see if I answer your question by talking, okay?
Oh, it's not a question. You've got W and, you've got W for women and you choose.
I should probably be consistent and use Fs. Yes, thank you. So, female and tall, female and short, yep. Okay, how about male and tall? What's that? 0.5 times 0.75. Great, which works out to be 0.375. And then this one's going to be male and short. So that'd be 0.5 times 0.25, which adds up, which multiplies to 125, yep. Okay, awesome. Now what happens, just this related thing, what happens if you add up all those probabilities? What do they add up to? That's how you know you've done it right. Okay, so you can check and see if the ends of all your branches add up to 1, then you know you did them all right. Is that first? So we're good so far? Okay, so the question, now go back to the original question. We wanted to find probability of female given tall. The basic rule to do that was what?
FNT over probability.
FNT over probability of T, right?
Yeah.
Okay. Now I know, but okay. F and T, like that event is the ends of one of these tree branches, right? Which one? The first one, 0.075. Okay. Okay. And then, now probability of tall. Is that one of the branches at the ends?
0.15.
It's, say that again?
0.15.
How'd you get that?
The probability of women that are tall, or do you add just like?
You have to add them. So maybe you're thinking that, you're just not saying it quite right, or maybe I'm misinterpreting what you're saying. So if you're tall,
Yeah.
you're either
So
woman and tall or you're man and tall, right?
Oh, okay, so,
So
yeah,
it's
that's a 0.375.
This one and that one. Do you see that?
Oh.
So that's, yeah. So 0.075 and 0.375. Does that make sense? If you're tall and you're a woman, or you're tall and you're a man, right? So that's how you get that. So you probably should write a little note in your notes as to how the heck you did that, right? This is tall and woman. This is tall and man. And that's how you found that number. Those two things added together. And you end up with 0.167. So if you have someone above that height threshold, the chances of them being female is 16.7%, as opposed to knowing nothing about their height, just 50-50, right? I don't know, I kind of, after doing this problem, I feel like I kind of like the tree one a lot. What do you like better, table or tree? Tree, yeah, so I won't specify on your quiz. I'll say use a table or a tree, I don't care. So, doesn't matter to me, but I think I like this one better too. Less writing. Okay, well let's do this one that way then. Oh, I didn't edit my slides. Crap. Okay, stop. Because you guys are grown-ups and you can all read, right? Yes, okay. So example 7 is another one of those breast cancer ones. Now, do I want to do that? Let me think for a second. I think I'm gonna skip that one because we already did one like it. And it's just like what we did with, so what the notes that I put online, they have a table there. If you want to see if you can do the tree thing correctly again, try to do it with the tree and see if you get the same answer. Does that make sense? Okay. So pause. So, which of the following sequences resulting from tossing a fair coin 5 times is more likely? So, 5 heads in a row, a heads, tails, tails, or assuming that the last one only had 5 things in it, not 6. What's the chances? Like, which one is more likely?
Middle one?
None of them. So if the question had been, what's more likely, throwing all 5 heads or 2 heads and 3 tails, then 2 heads and 3 tails is more likely, right? But the probability of getting this exact sequence or that exact sequence, they're the same. Because the second sequence also has to happen in that particular order. Does that make sense? So even though the second and third ones seem more randomish to you, they're actually not any less likely. So yeah, all have the same probability. And this is kind of related to the stuff we were doing last time. If you flip a coin 5 times, how many events are in your sample space S? How many choices for the first coin? 2 times 2 times 2 times 2, so 2 to the 5th, which is 32, right? And each of those outcomes is 1 out of those 32 outcomes, right? So the probability of all these is equal to 1/32. That's just... But if it's a probability of 2 heads, then it wouldn't just be 1, it'd be many things have 2 heads. But that specific sequence is just as unlikely as heads, 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 heads. Okay. Suppose a friend has 3 boys and would like to have a girl, and she says because she has already had 3 boys, she's definitely going to have a girl next. That's how one family in my hometown got 6 girls. So,
That's how you end up with like 10 kids.
exactly. So, is this person right? Definitely not. No, 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 no. The chances on the next baby are still half and half, right? Maybe even the fact that she's had more like boys in a row means there's something else up with her and she's only gonna have boys. So, yeah. Maybe it's her husband's fault.
Coming from a biological standpoint.
Yes, but we'll say it definitely is her husband's fault for sure.
Oh, yeah, always.
It's always the husband's fault. Okay. So the next one you have is about people in a room and birthdays, right?
Yes.
Okay. And I think I said that there are 20 people in the room, right? Well, I want to make that smaller, okay? Because they'll be easier. I want to say it's 5. Suppose there's 5 people in the room. What is the probability that at least 2 have the same birthday?
Didn't the percentages go significantly down compared to 20 then? 'Cause we
It
all-
will, but yeah, but I was just going to tell you how it would generalize to 20. Does that make sense? Okay, so at least 2 same.
Would it be 1 over 365 squared?
Not quite, because that would actually be that they're,
Because that seems really small.
yeah, it's much higher than that. So let's do it with complements. The probability that none are the same. So how many choices for the first person's birthday? 365, right? Does that make sense? How many for the next person's birthday? And we are like, we're totally ignoring leap years, okay? Because that makes it harder. And then the next person's birthday is 363, and then 362, and then 361, right? There's the 5 people.
Remind me why we're going down again?
Because once you've picked a birthday, that birthday can't be chosen again, and it reduces your possibilities. Okay, and just like with the dice flipping, or the coin flipping, there's 2 chances, right? 2 events, so it was like 2 to the 5th, right? For birthdays, there are how many total choices for one birthday? 365. And because you do it for 5 people, the total is 365 to the 5th, which is going to be humongous. You put it in the calculator, and that's 0.973. So that's the chances that no one shares. So 2 people, at least 2 people sharing is the opposite of nobody sharing. Does that make sense? So probability that at least 2 are the same will be 1 minus probability of none. So 1 minus 0.973 works out to be 0.027. I'll talk about what would happen if I had 20, and then I promise I'll stop, okay? So if I'd had 20 people, you do it the same way, right? Except for what's gonna suck more. The bottom's gonna be 365 the 20th. The top is gonna be 365, 364. Let's think, how far down do we go? Okay, so this 365 minus 5 is 360, right? The last number we had there was 361, 1 more than that, right?
So it'd be 346.
So it'd be 346. Yep. Does that make sense? Which comes out to be actually quite high, 0.587. So once you get 20 people, the chances that they share goes up quite a bit. 1 minus that number comes to be quite high.